Chapter 5 is on ionic compounds. An ion can be either an individual atom or a group of atoms that has a charge, and it has a charge because it's either gained or lost electrons. So nothing changes about the neutrons or the protons. The only thing that is different is going to be the number of electrons. If it's an individual atom that has become an ion, we call it a monatomic ion, and a group of atoms that has a charge is called a polyatomic ion. So, for example, here I have listed sodium's electron configuration. This would be the sodium atom, just the neutral atom. Its electron configuration would be 1s2, 2s2, 2p6, 3s1. So the only electrons that we're going to be paying attention to are the ones in the outermost energy level. Those are the valence electrons, and those are the ones that will be involved in the bonding or the forming of ions. So these 3s1 electrons are going to be given away for the sodium atom to become the sodium ion. Okay. Now once it has been given away, what's left over is going to be the sodium ion, and the only thing that's going to be different here is that there's no longer a 3s1 electron. Now the next outermost energy level, the second one, is going to have 8 valence electrons total to make it stable. If an ion is positive, we call that a cation, and that means that the neutral atom has lost electrons because it's lost negative charges. All of our metals are going to form cations, and then our nonmetals are going to form anions or negative ions, and that means that they will be gaining electrons or gaining negative charges. A couple terms in this section: electroneutrality, which means that you're going to have equal numbers of positive and negative charges. So wherever there's a positive charge, there's a negative charge somewhere to match it. And then isoelectronic means that elements can have the same electron configurations as each other. So for instance, the sodium ion that I was just talking about, when it becomes that sodium ion and loses its 3s1 electron, it now becomes isoelectronic with neon. So this is neon's normal electron configuration, and once sodium starts changing its numbers of electrons, it will be isoelectronic with the neutral neon atom. The octet rule means that atoms tend to gain or lose electrons so that their outer s&p orbitals or main group orbitals are filled with 8 electrons. So that's always the goal, is to get 8 electrons total so they can be stable like the noble gases. Now for the main group elements, it's easy to count across the number of groups to figure out how many valence electrons an element would have. So group 1 has 1, group 2 has 2, 3 has 3, and so on, all the way until you get to 8, which is our noble gases. And once you know how many valence electrons they have, then you can figure out what their charges will be. Take group 1 again, for instance. They have 1 valence electron, and it's easier to lose 1 electron and become a positive ion than it is to gain 7 electrons. It takes less energy to do that. So the group 1 will all become positive 1 ions, and you can follow that same pattern across those main group elements. Now, the transition metals, or our D-block elements, those ones have some differences. They don't follow a regular repeating pattern the way the main group elements do. So in order to know what their electrons are going to be doing, we use Roman numerals to designate which type of ion they're forming. So for instance, iron can form 2 different ions. It can be iron 2+ or iron 3+. So to specify which one we're talking about, we would write that as iron 2 with the Roman numeral 2 in parentheses after it, or iron 3 with the Roman numeral 3 in parentheses after the word iron. Ionic compounds are just going to be combination of elements that have opposite charges. So you're going to have a metal that is a positive ion combining with a nonmetal or negative ion. So the metal will transfer its electrons from the metal itself to the nonmetal. Binary ionic compounds means that you only have two types of elements that are present in that particular compound. So the examples here, I have zinc sulfide or potassium bromide. There's only two types of elements that are present in these particular compounds, so they would be binary ionic compounds. Now, to name binary ionic compounds is a relatively simple process. You always start with the cation, which will be listed first in the formula, and then follow it by the anion. So for this particular one, we have CaS, so we're going to look up what Ca means, and that can be calcium, and then we're going to look up our anion, which is S, and that is sulfur. And then the only thing we have to do at the end here is to change sulfur's ending to IDE. So this actually becomes calcium sulfide. So it's name the cation, name the anion, and then change the ending to IDE. Here's a couple more examples. We have Al2S3, that's going to be aluminum sulfide. And notice I'm not doing anything with the 2's and the 3's. I'm not putting prefixes like dialuminum, trisulfide, nothing like that. It's just state the cation, state the anion, and change the ending to IDE. The second one here, we have Rb2O. Well, Rb is rubidium and O is oxygen, so we change that to oxide. And now these last two involve a transition metal, a D block element. So we have to specify what the charge is going to be. So for this one, we have FeF2. Okay, well, we know that Fe is iron, but we don't necessarily know what its charge is yet. So if we look at fluorine, fluorine has 7 valence electrons, which means that it will gain 1 more in order to achieve an octet. So fluorine will always have a -1 charge. Now, in an ionic formula, you need to always make sure your positive charges equal out with your negative charges. So if we've got 2 fluorines, each of those with a -1 charge, then that means that our iron must be a +2 in order to balance that out. So we know that this must be the iron 2 ion, so this formula is iron 2 fluoride. Same thing with chromium down here. Iodine is a 1-, just like fluorine, they're in the same group. And I need 3 of them to balance out 1 chromium. So this must be chromium 3 iodide. Now when it comes to writing formulas, it's simply going in the opposite direction. So this time you might be given the name and you will need to come up with the symbols. So again, the first one listed is always going to be your cation. So aluminum we would look up is Al, and it is in the 3rd main group, so it's going to be a 3+ charge. And oxygen is O, and it has a -2 charge to it. So we need to balance those charges putting subscripts in. So if Al is 3+ and oxygen is 2-, well, the least common multiple between those is 6. So if I'm going to get 6+, that means that I need 2 aluminums. And if I'm going to get 6-, that means I need 2 oxygens. So my formula is going to be Al2O3, and that will neutralize my positive with my negative charges. You can also look at it as crossing down these charges. So for instance, I have aluminum here and oxygen here. I could take this 2 from oxygen, cross that down to be the subscript for aluminum, and then cross the aluminum's charge down to be the subscript for oxygen. And that will give you the same result, Al2O3. Here are a couple more examples of that. Calcium oxide. Well, calcium is a 2+ and oxygen is a 2-, so they are actually already balanced. Now, if you wrote the charges in and cross them down and put Ca2O2, then you would simply keep reducing that. With ionic compounds, you can reduce those formulas down. With potassium nitride, potassium is a +1, nitrogen is a -3. So you would cross that 3 down, and you have K3N. Here we've got a D block element, tin 2, so that means that tin is a 2+, oxygen is a 2-, so they're already balanced, so you'd simply write SNO. And then the last one is copper 1 bromide. So copper is a 1+, that's what this Roman numeral is telling us. Bromine is a 1-, so they are already balanced, so we write CuBr.